Now for acids and bases. According to textbooks, acids are anything that release an H plus ion. Keep in mind, H, we covered hydrogen before with atoms. Hydrogen atom, remember, had a proton and one electron orbiting around it. In that configuration, remember what drives chemistry is that every atom wants to have a full outer shell. So hydrogen is looking for a second electron, one to fill its outermost shell. Doesn't care how it gets it. Okay, now it's a weak man on the totem pole, and so it has a hard time getting electrons. It really can't steal them, but it can share them, as we've seen. The issue comes, it makes hydrogen somewhat chemically reactive. Think of it like money. If you're doing your monthly budget, and you come to the end of the month, and you're $100 short of paying your bills, you are adamantly looking for money. Correct? Sorry. And then adamantly looking for, you're looking in your pants pockets, your coat pockets, underneath your couch, you're emptying your change jar and to get the money. Now what having this hydrogen become H plus is it lost its electron. So it's not one electron short of a full outer shell, it is 2 electrons short. So that's like the following month, you're not $200 short, you're $1,000 short. So how adamantly you're looking at money, you're calling up. And what was that commercial about donating plasma? How much money do you get for that? Mom, dad, some second cousin you haven't seen since you were 10 years old. Can I borrow some money? You call Susan that you loaned money to go to a movie in 7th grade with interest. You owe me $35 by Friday. So you're very adamantly. So this hydrogen's very adamantly looking for electrons. And electrons don't have VIM numbers, so it's not going around saying, have you seen my electron? Here's a picture, here's the VIM number. It doesn't care whether it gets the electrons from your paper, the tabletop, your shirt, or your skin. So it's highly chemically reactive. As everybody knows about acids, they are highly chemically reactive and they react quickly. As they burn, of course the chemical reaction is going to happen, or is happening. Now they also, if you get on your shirt, you're worried about more than just your shirt, and that's because these also penetrate. And H plus is basically the smallest particle, independent particle we can have. It's just a proton. Electrons, remember, are usually on atoms or ions or isotopes. We don't go and weigh out 6 grams of electrons, but we can have protons in a solution. And in this case, they can get between the fibers of your clothing. And it's like the Grand Canyon. And they can get between the skin cells of you. And because that's like I-45 corridor. So they have no problem. So they penetrate quite readily. And that's what makes them, they're called fast burners. And everybody knows when you've been burned by an acid because, ow, it hurts. In lab, we generally have a rule that if you get injured, you have to come see the professor first, unless you're being burned by an acid. We'll know that you're being burned by an acid as you knock over chairs and people trying to get to the sink to wash the acid off of your skin. Now, bases, on the other hand, are the opposite. Some define them as they release OH minus ions, and that's true for most. But there are a couple exceptions. They all absorb H plus ions. They are the counter agent to acids. Even something like ammonia, NH3, will absorb NH plus, absorb H plus to become NH4 plus 1, ammonium ion. These are in a salt, so like sodium hydroxide, potassium hydroxide for that. Now hydroxide has OH minus. OH, it's a little bit bigger molecularly, or a lot bigger than a proton. And of course the negative means it has an extra electron. So it's also chemically reactive, although sort of like the next month you find yourself that you have an extra $100, you are not very adamantly trying to spend that. You're not going around, ooh, do I owe you money? Do I owe you? Call Mom, Dad, do I still owe you money? oh, maybe I'll pay back my student loans early. But if you're like me, by the 7th or 8th day, you've spent the money. So bases are what we call slow burners. And actually, they're considered more dangerous than actually acids because, as we mentioned, you know when you're being burned by an acid, but you do not know when you're being basically burned by a base. They're deceptive. They feel slimy for the most part. And you see students over there, they get a little base on themselves and they're just sliming their hands together and wondering if that's how Ghostbusters is. Ooh, it feels funky. And we always tell students, the golden rule is wash your hands at the end of lab. And they won't. Some of them don't. And they learn the hard way because they'll be sitting in history class 3 hours later as their hands are getting red and swollen and itchy. And that's not good. As you probably heard, and we've talked about already, is acids and bases are counterparts of one another. So when you add an acid and a base, we have that exchange reaction take place. As we see down below here, the H plus from the acid and the OH minus from the base will come together to form water, H2O. And what they'll do is switch partners with the salts that brought them. So if we have hydrochloric acid, we have chloride left, and we'll have sodium left from the sodium hydroxide, and that gives us sodium chloride, table salt. So again, we see an example. Two harmful things, an acid and a base, actually will recombine to form two useful things your body needs, salt water. How much acid is not in a solution is very important to chemistry, especially for living things. And so scientists had to come up with an easier way to talk about how much acid is or is not there. So hence they came up with the pH scale. Negative log base 10 of the hydrogen ion concentration, which sounds kind of bad, but really it's not. The log base, well, actually, when you talk about concentrations, if we want to talk about concentrations, we can put these in whole percentages, tenths. So a 10% solution would be a 0.1 solution. 1/100th would be 0.01. 0.001. We just keep on going by that. Go down further, all the way down to 0.00000001. That's kind of hard to deal with because if you're reading through the textbook, and the difference between 0.000001 and 0.000001 would be easy to miss. So we can think about these as exponents. 1 times 10 to the minus 1, 1 times 10 to the minus 2, 1 times 10 to the minus 3. Jump down a few, 1 times 10 to the minus 7, all the way to 1 times 10 to the minus 14th. Again, that's a little bit difficult, so I want to make it easier. The log base 10 is simply taking this exponent, the minus 1. Okay, we're going to take that minus 1 number. There we go. Now the problem with this is we have a negative number representing something that is there. Remember, negative represents something, imaginary number, less than 0, so less than nothing. And so that's why it's a negative log base 10, because a negative times a negative gives you a positive. So this would be a pH of 1. 1 times 10 to the minus 2, that would be a pH of 2. 1 times 10 to the minus 3 would be a pH of 3. As I said, when you're covering negative numbers in math class, they usually gave you story problems, but not when you cover negative numbers. They never say, Susan has 3 apples. She eats 7 of them. Minus 4? We owe her 4 apples? No, she's going to eat 4 apples tomorrow? Okay, it doesn't work that way. Negative numbers only exist in math class and bank accounts. I can attest to both of those. I've taken math. Okay, 1 times 10 to the minus 7 would be pH of 7. Of course, 1 times 10 to the minus 14 would be pH of 14. So our pH is going to range from 1 to 14. The real tricky thing, the thing you got to remember, write it down the margin, okay, whatever, is notice that scale seems backwards. As the number gets smaller, you actually get more acid. That's the tricky part about this. The lower the number, the more acid, because we're dealing with the opposite side of the decimal place. So please keep that in mind. So 7 is neutral, and I'll show you why. We said that H plus and OH minus will join together to make water, and that's true. But it's a reversible reaction. So any body of water, whether it be a water bottle you have, a pond, the Gulf of Mexico, any body of water will break down into H plus and OH minus at a rate of 1 times 10 to the minus 7. Now that's going to be neutral. That's going to be a pH of 7. That's going to be neutral because you're making an equal amount of acid and equal amount of base. Now if from whatever source you start adding more acid, the acid amount will increase, and of course we just said your pH will decrease. The acid will react with base, the hydroxide, and become water. So as more and more acid's added, the hydroxide's going away. It's like a little teeter-totter. So we add more on one side, we decrease the other side. If we add in a bunch of base, just the opposite happens. As the base increases, a bunch of that will react with the acid, removing it from the solution. So as base increases, acid decreases. And so again, the pH now goes up. Remember, opposite. Acids and bases can be described as strong. Strong acid or bases, when they're put into water, dissociate 100%. Hydrogen chloride, okay, HCl, when you put it in water, 100% breaks up into H plus and Cl minus. You get all the acid from that ion. Sodium hydroxide, for that base, same thing, 100%. A weak acid or base only breaks up about 30%, plus or minus, like carbonic acid. Carbonic acid put in water, 30% will break up and release H plus and bicarbonate. 70% will stay as the original molecule. Concentrated versus dilute acid, of course you probably already know these. Have to have some easy questions on the exam. Concentrated, like when you buy juice concentrate, of course it's going to have a higher percentage of that acid or base in there. And dilute has mostly water, so a lower percentage. I mentioned before that pH is very important, the amount of acid that is or is not there. So much so that, again, homeostasis, you have to keep a certain range, and in nature it does that using molecules known as buffers. A buffer stabilizes, underline, circle, highlight this in your notes, stabilizes, not neutralize, stabilizes a limited amount around a certain pH. Every molecule will be different. None are at 7 as far as I ever heard. 7.4, 6.8, 11.2, 13.1. Okay, all over the scale. It acts as an acid and base because a molecule, if you add acid, it can absorb H pluses. Now, once you exceed how much that molecule can absorb, now, depending on how many molecules, the more buffer you have, the more it can absorb. Once you exceed what it can hold, the pH will start to change. More acids there, and so the pH will start going down. If you now add base, the buffer will give up the acid, and the acid will combine with the base, making water, keeping the pH the same. Once you exceed the acid that the buffer's holding, again the pH will change, and of course now it'll start going up with more and more base. For example, the homeostasis, the range for normal blood pH, I think I mentioned in the first lecture, 7.35 to 7.45, very narrow range. We use 3 major buffers and about 5 minor buffers actually to make certain we keep within that range, because it's very, very important for how proteins function in the bloodstream. If your pH starts getting too high, that's called alkalosis. You're going outside that range and you're getting sick. You go too far, of course, you'll die. On the other sense, if you start getting too much acid, that's called acidosis. If it starts becoming too low, of course it can make you sick and eventually die.